Hey guys, so in this video I want to show you how to solve a very particular type of problem. Problems where we're going to have objects moving over humps or bumps, and basically it's going to be a box or a car that is going to be moving and then it goes over a hump like this. All right, let's check it out. So I have three questions here, or three parts, all revolving around this same situation here, which is we have a car riding over two consecutive bumps or humps. Consecutive means one after the other. They're nearly circular. Nearly circular means that even though it's not perfectly circular, we're going to treat it as if it was. So you can basically ignore the word nearly there. And they have radii of RA and RB. So this is RA right here, the distance from the center of the circle to any of the edges. And then RB right here. Okay? And right away, one thing that I want to point out is that this means that this distance here is RA as well. So if you think of this as being the floor, then the height at point A is the same as RA. Okay, same thing with RB over here. If you think of this as the floor, then the height at point B is RB. And that's going to be useful a little bit later. All right, so here I want to derive an expression. Derive an expression means we're going to have, we're not going to have any numbers, we're just going to have variables everywhere. For the maximum speed, so that the car can have at the top of the second bump right here. So what is Vmax B in order to not lose contact with the road? In order to not lose contact with the road. I want to remind you that lose contact in a situation like this, if you lose contact, it means that the normal force became zero. Okay? Now, in these problems, the way we're going to set them up, it's a little bit counterintuitive. We're actually going to set it so n equals 0. Now you might be thinking you want to move in such a way that you don't lose contact. You want to move in such a way so that your n is not 0. Why would you set it up so that n equals 0? Well, and that's the reason we do this, is to find basically our boundary conditions, or basically the line at which you would either be 0 if you're a little bit faster, or not 0 if you're a little bit slower. Basically the tipping point around which you're about to lose your contact with the road. Okay. Another way to think about this is that so that you can find out at what speed you would begin to lose contact with the road, so that you know to go a little bit slower. Okay. So again, remember, in these problems they are sort of counterintuitive. Even though losing contact means normal equals 0, we want to set it up in that way. We want to set up normal to be 0. Okay, so normal at point B will be 0. That's the first point I want to make. The second point I want to make, really important, is when you have these problems where you have an object going around a circle, there's two ways you could solve them. Okay, so when you have these circular motion problems, there's two ways you can solve. Now, when I say two ways, only one of these two ways is correct. But depending on a little detail, you would pick one or the other. Basically, if the problem refers to only one point, then you're going to use the sum of all forces equals ma. And that's what's happening with this question here. In this question, part A, I'm saying what is the maximum speed at B, right there, so that you don't lose contact with the road at point B. Everything in this problem in part A is referring to the same point. Everything is referring to point B. So because we're only referring to the same one point, we're going to use F equals ma. If I was referring to 2 points, we would use energy to solve this. What would that look like? Well, something like part B. Part B says find the maximum radius here so that you don't lose contact here. It's talking about 2 points, so we're going to use energy. Okay, so 1 point is F equals ma, 2 points is energy. One way to remember this is that F equals ma has to do with the forces, centripetal forces at 1 point, equals ma, the acceleration at the same 1 point. The energy equation, however, has k initial plus blah, 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 all the way to u final. The energy equation always has to do with 2 points. F equals ma always has to do with 1 point. Okay, so because we're talking about the same point here, we're going to go with this. Sum of all forces centripetal equals ma centripetal. And this is at point B right here. So what are the forces at point B? There's mg pulling you down and there's normal pushing you up. Normal plus mg. We haven't done signs yet. Let's talk about that now. In centripetal problems, in centripetal force problems, forces going towards the center are going to be called positive, so mg is positive, and away from the center will be negative, so normal is negative. Okay. Now, once you start writing this, one of the things you might be confused about is that, well, why would I use F equals ma if I'm looking for velocity? There is no velocity in F equals ma. Well, actually there is. Remember, AC is v squared over r. So instead of writing AC, I'm going to write v squared over r. And the reason for that is I want to solve for v. The only way I can solve for v is obviously if it shows up in the equation. So we make it show up in the equation so that we can then solve for it. Last thing I got to do here is remember we said that normal was going to be 0 so that we can find at what speed you would begin to lose contact with the road. Okay? If I simplify this, I get mg equals mv squared over r. Notice that the masses cancel and we're left with v equals the square root of gr. Okay, so just as an example, if this number turned out to be, you don't have to write this, that's not the answer, but if this number turned out to be a 10, this means that at 10.001, you're going to fly off, but at 9.999, you're going to make the turn because you're not going too fast, right? If you drive too fast over a speed bump, what happens? You get shot off, right? So you just fly away for a little bit. Don't do that. Cool, and then the other thing here is just the last touch up is that this is the radius. There are two radii, RA and RB. We're talking about point B, so this is the radius at point B. This is the final answer, and I want to quickly point out to you that this is very similar to our loop-the-loop or roller coaster problems. If you've done one of those before, it looked kind of like this. And again, if you've done it, at some point I asked, what is V min top? What is the minimum velocity at the top so that you don't lose touch with the tracks? Or it could also be water inside of a bucket and you were spinning it vertically. What is the minimum velocity? If you did this, the setup was the same. You did normal equals 0 and you ended up with V min top being the square root of GR. The answer is exactly the same, I'm going to put this in parentheses here, as this. The only difference is that this is the minimum velocity so you don't fall. Here, since we're going like this, it's actually the maximum velocity so that you don't shoot out of the path like that and lose contact with the road. Cool. Very similar setup. Let's move on to part B.